Now let's take a look at how we can verify and simplify trigonometric identities. So let's talk about how we might verify that a trigonometric identity is true, or maybe even prove that it's true. A good step one is to pick one side of the equation and work only on that one side. It's better to start with the more complex side, as that's the side that gives you more to work with. Step two, you want to look for some opportunities to maybe factor an expression, square a binomial, or even add fractions. Step three, you'll want to note which functions are in the final expression and look for opportunities to use those identities and make the proper substitutions. And step four, one that I use a lot, is convert all terms to sine and cosine. So let's take a look at an example. In this example, we're being asked to verify that the cosecant of an angle times the cosine of the angle times the tangent of the angle is equal to 1. Now, this is not an identity that we know of. It wasn't on our list of identities, but we want to prove and see maybe this is a new one. So the first thing that I'm going to do is pick a side. And I'm going to pick the left-hand side because it definitely looks like there's more for me to work with. Then I'm going to convert everything that I see in terms of sine and cosine. So the cosecant of theta is going to become 1 over the sine of theta. And the cosine of theta is already as a cosine. And the tangent becomes the sine of theta over the cosine of theta. And I want to prove that that equals 1. So the question is, does it? Well, that cosine that was in the middle is over 1, isn't it? And so now if I think about multiplying straight across, I'm going to have in the numerator 1 times the cosine of theta times the sine of theta. In the denominator, sine of theta times 1 times the cosine of theta. Or I know in multiplication, I can cross reduce. So I see in that first factor, the sine of theta in the denominator, I can cancel that with the sine of theta in the numerator. Same thing goes for the cosine. And what I'm left with is the statement that 1 equals 1, which is a true statement, and therefore verifies this identity. Let's look at another example, and in this example, we're being asked to simply simplify a trigonometric expression. That's different than what we did before, where we verified that a trig identity actually equaled something. Now, we will be doing the verification, but in the process of doing the verification, there's a lot of techniques that we can learn about simply by simplifying. So the first one says to simplify the sine of an angle t over the quantity 1 plus the cosine of angle t. And the technique that we want to look at here is the technique of multiplying what we call a well-chosen one. Now, a well-chosen one simply means that it is equivalent to 1 but doesn't necessarily look like 1. So for example, probably when you first learned about adding fractions, you had to find a common denominator, right? So for example, maybe you said, okay, well, what is 1/2 plus 1/4? And you couldn't add those straight across because they have different denominators. And so what you did was you multiplied that 1/2 by 2 over 2. And the reason why you did that was because now you had 2/4 plus 1/4, and now you could add the fractions to get 3/4. That 2 over 2 is what we're talking about when we say a well-chosen one. It's a well-chosen one because it helps us simplify or take that expression further. It's equal to 1, even though it doesn't look like 1. It's equal to 1, and therefore it's not changing any of the values. Okay, so let's do that with this one. So I'm going to start by writing the original problem down. So I'm going to say the sine of angle t over 1 plus the cosine of angle t. And what I'm going to do to simplify this, and sometimes it's hard to know, what am I simplifying to? So I'm oftentimes just trying to do something, what can I do to this? I can't rewrite anything in terms of sine or cosine because it's already in terms of sine or cosine. So I'm going to multiply by a well-chosen 1. And in this example, my well-chosen 1 is going to be the conjugate of the denominator. Now, conjugate is something you've probably worked with, but let me refresh your memory. The denominator of this expression is 1 plus the cosine of t. The conjugate is exactly that same thing, only instead of plus, it's going to be minus. Okay, so it's exactly the opposite in terms of that middle value. And if I do that on the top or the bottom, then I have to also do that on the bottom. Okay, so this is called the conjugate. Now, why the conjugate works so well is because what ends up happening is we end up multiplying a binomial like a plus b, we end up multiplying it by something that looks like a minus b. And you may remember this from previous classes that when you FOIL this out, you get a to the second power, so you get a times a, and then you multiply a times minus b and a times positive b. Those two terms cancel out, and then when you multiply the ends, you get minus b squared. So it really helps to eliminate some of the terms and therefore simplifies, which is exactly what we want to have happen here. All right, so let me do that. Up in the numerator, I'm going to leave this as the sine of t times 1 minus the cosine of t times that whole quantity. And down in the denominator, when I multiply 1 plus the cosine of angle t times 1 minus the cosine of angle t, I get 1 minus cosine squared t. And the reason that looks so much smaller than you might expect is because of the relationship that we talked about over here with the conjugate, where when you multiply the two binomials, the middle terms end up canceling out. Now, from this point, what else can I do? Well, 1 minus cosine squared t. So anytime I see something like cosine squared, I am immediately thinking about the Pythagorean identity. And the Pythagorean identity says that sine squared of some angle plus cosine squared of some angle is equal to 1. Now, if I subtract cosine squared theta from each side, I will end up with the fact that the sine squared theta is equal to 1 minus cosine squared theta. Now, what that means is that down in the denominator, this whole part, I'll just circle it for us, this whole part right here is in the same form as a variation of the Pythagorean identity. So I can say, I'm just going to rewrite the sine of t. I'm going to rewrite that numerator. I'm not going to multiply anything through at this point. And that's going to equal that 1 minus cosine squared t is going to simply turn into sine squared of t. Now, because I have multiplication in the numerator, that means I can do some canceling. Up in the numerator, I have sine of an angle. Down in the denominator, I have sine of an angle times sine of an angle. So one of those sines cancels out. And I am left with, up in the numerator, 1 minus cosine of the angle t, and down in the denominator, the sine of t. Now, does that look any more simplified than what I started with? Maybe not necessarily. I could probably do one more step. I'm running out of room a little bit here, so let me just put it to the side. 1 minus the cosine of an angle divided by the sine of an angle is the same thing as 1 over the sine of the angle minus the cosine of the angle over the sine of the angle. And that is because this sine of t belongs not only to the 1, but it also belongs to the cosine of t. And that's going to allow me to do my final simplification, because I know that 1 over the sine of t is equal to the cosecant of t, and I know that cosine over sine is cotangent. And so I started with the sine of t over the quantity 1 plus the cosine of t, and I can now say that that is equal to the cosecant of t minus the cotangent of t. All right, let's try another one. In this example, we're asked to simplify 1 over 1 minus the sine of an angle plus 1 over 1 plus the sine of an angle. So those denominators are conjugates, aren't they? Now, what we're going to show in this example is the technique of rewriting an expression with a common denominator. What we have are two fractions, right? We're being asked to take the first fraction and add it to the second fraction, and those denominators are not the same. So we can't do anything with this until we find that common denominator. So I'm going to say that 1 over 1 minus the sine of theta plus, I'm going to just leave a little bit of space here, 1 over 1 plus the sine of theta, that in order to do this, I need a common denominator. So my common denominator is going to become, I'm going to multiply by the conjugate, so 1 plus the sine of theta over 1 plus the sine of theta. I'm going to multiply. And to the second piece here, I'm going to multiply 1 minus the sine of theta over 1 minus the sine of theta. This is exactly same technique as I showed on the last slide, where we had a fraction and we could not add unless we had a common denominator. Maybe something like, what if I said, what is 1/2 plus 1/3? You would have to take this fraction and you might multiply the 1/2 by 3 over 3, and you might multiply the 1/3 by 2 over 2. That's exactly what we're doing in this example. Okay, so what does that equal is the question. So what does that equal? Well, if I take a look at this first piece, I'm going to get 1 times 1 plus the sine of theta. So I'm just going to call that 1 plus the sine of theta. And my denominator, what is 1 minus the sine of theta times 1 plus the sine of theta? We know that when we take a binomial, like 1 minus the sine of theta, and we multiply it by its conjugate, that when we FOIL it out, that those middle terms will cancel out. So I will be left with 1 times 1, which is 1, and the middle terms cancel out, and I'll be left with minus sine squared of the angle. Now notice I wrote that sort of in the middle because I know that that's going to happen not only in this first term, but it's also going to happen over here with this second term. So all I need to do now is figure out what the second piece here is. So what is 1 times 1 minus sine of theta? That's simply going to be 1 minus the sine of theta. All right, now what should I do? See anything that I can simplify? I like that up in the numerator, it looks like the sine of theta and the minus sine of theta will cancel out. That's nice. So up in the numerator, I'm left with 2. Now, what can we do with that denominator? What does 1 minus sine squared theta equal? So hopefully you watched carefully on the last slide, and you remember that I said that anytime I see this square, I'm thinking Pythagorean identity, and I know that the variation of the Pythagorean identity is that I can let 1 minus sine squared theta be equal to cosine squared theta. So this is a big simplification. I can say that the original expression of 1 over 1 minus sine of theta plus 1 over 1 plus sine of theta has simplified all the way down to 2 over cosine squared theta. Can I take this any further? And the answer, I think, is yes, because Here's what this is equal to. This is equal to, we know, let me just write this off to the side. We know that 1 over the cosine of theta, what is that equal to? Well, that's equal to the secant of theta, isn't it? So here's a way to think of this. I could call this 2 over cosine squared theta. I could think of that as 2 over cosine of theta times 1 over cosine of theta. Or maybe, actually, let me do this. Let me do it like this. Let me say that this could be equal to just 2 times 1 over the cosine of theta times 1 over the cosine of theta. And that's going to equal 2 times the secant of theta times the secant of theta, which I can call secant squared. And so I think that looks pretty good, and I'm going to stop right there. Let's look at another example where we're being asked to simplify a trig expression, and we're going to look at another technique that helps us to do that, and that technique is factoring. And in this example, I'm going to show you 2 ways that I could approach this problem. All right, so let me start by writing out the original problem, which was 1 minus cosine squared of x over the sine of x plus the cosine of x times the sine of x. And I want to factor this. All right, so 1 minus cosine squared of x. This is where I feel like I could do one of 2 things. I could either rewrite 1 minus cosine squared of x as sine squared of x, which I'll show you. That's the variation of the Pythagorean identity. Or I could factor that numerator to 1 plus the cosine of x times 1 minus the cosine of x. Right? Those are the 2 things that I could do on this. And I'm going to show you that because in this situation, they're not asking me to prove that this original problem equals a specific thing, then I can really do either way, just as long as I rewrite it, basically. In my denominator, I have 2 terms that have a common factor. So I'm going to factor out the sine of x, and when I do that, I'm left with 1 plus the cosine of x. And in fact, that is exactly what I would do for the other approach as well. I would factor the sine of x out and be left with 1 plus the cosine of x. Okay, so here's where it looks a little bit different, because in the first simplification, I have, oops, and I forgot to put my fraction bar, didn't I? I have, up in the numerator, I have sine squared x, which is sine of x times sine of x, and I have a factor that I factored out, the sine of x. So this sine of x is going to cancel with one of the sine of x's in the numerator. That's going to leave me with the sine of x up in the numerator over 1 plus the cosine of x in the denominator. And I think that that's all I can do. Now, I'm going to put an equal sign here, but I'm equaling the thing that's right above it. I'm not necessarily equaling the thing that's to the left of it. In this example, the thing that's going to cancel out will be the factor of 1 plus the cosine of x. That's going to factor out of the numerator and the denominator. And I'm going to be left with 1 minus the cosine of x up in the numerator, and down in the denominator, I'll be left with the sine of x. These look a little bit different, but they both should be simplifications of the original expression. There's not necessarily one that's more right than the other. In this case, you're not being told much other than simplify, so either one of these could work. I will say for the second approach that I could take this one step further, couldn't I? I could distribute that sine of x belongs to each one of the pieces of the numerator. So I could rewrite this as 1 over the sine of x minus the cosine of x over the sine of x. And that would give me the cosecant of x minus cotangent of x. So that would break that down just a little bit more. Either approach would work. And because both equal that original expression, we could probably, and we won't do it here, but we could probably make the case then that each one of these must equal each other. And that might be something you want to try on your own. Now let's look at an example where we're asked to verify a trig identity. I personally find these easier because we are being asked to prove that one side equals another side in an identity. In this example, the cosine of beta over the quantity 1 minus the sine of beta, does that equal 1 plus the sine of beta all over the cosine of beta? So we know a direction, we know what we're headed toward. What's difficult in this example is that there's not a clear side to begin working on. Everything is already written in terms of sine or cosine, so we can't rewrite it that way. So let's use one of the techniques that we've learned in the previous slides. And I'm going to use the technique of multiplying by a conjugate, and I think I'll go ahead and start on the left. So working only on the left-hand side, and sometimes it might help you to even draw a line so that you know you're picking one side. I'm going to work on the left, and I'm going to say, I'm going to write that original side down. So the cosine of beta over 1 minus the sine of beta. I'm going to multiply that by the conjugate of the denominator. So 1 minus the sine of beta. 1 plus the sine of beta is the conjugate. I'm going to multiply that on the bottom, and I'm going to multiply that on the top. And what I'm hoping to do each step along the way is get closer and closer to turning the left-hand side into the right-hand side. Now, in the numerator, I'm going to leave that as the cosine of beta and multiplied by 1 plus the sine of beta. In the denominator, I'm actually going to FOIL that out. So we've seen previously that if I factor if I multiply 1 times 1, 1 times 1 is 1, and then 1 plus the sine of beta, and then 1 minus the sine of beta, those middle terms will cancel out, and then the sine of beta times the sine of beta is 1 minus the sine squared of beta. Down in the denominator, we know that 1 minus sine squared beta is cosine squared beta. So I'm going to rewrite that as cosine squared beta. And up in the numerator, I'm going to leave it as cosine of beta because I like the idea that maybe I can do some canceling here. And up in the numerator, that cosine of beta is being multiplied, so it's a factor, and it can be canceled with one of the cosines down in the denominator. That's going to leave me up in the numerator with 1 plus the sine of beta all over cosine of beta. And sorry, my pen did a weird thing with that sine of beta. Let me rewrite that. So 1 plus the sine of beta up on the top. Now you might notice that I haven't even mentioned what I'm trying to get that to equal to on the right-hand side. Basically what I'm trying to do is just do something. What can I do to alter the way this looks? And you'll notice that in this example, I actually have made the left-hand side look like the right-hand side. So my last step is to rewrite the right-hand side equal to the left-hand side and put a big check mark that feels very satisfying. Okay, so your very last step should show that one side really does equal the other side. All right, let's try another example. In this example, we're being asked to verify the identity, and this is a big one. Up in the numerator, sine squared theta minus 1 all over the tangent of theta times the sine of theta minus the tangent of theta. And does that equal, on the right-hand side, the sine of theta plus 1 over the tangent of theta? So the first thing to do is determine, do we want to work on the left or do we want to work on the right? And in my opinion, just looking at this, the left-hand side looks a lot messier than the right-hand side. So I like to work on that messier side because I feel like there's more for me to do. Now, the technique that I'm going to use here, sine squared theta minus 1, that could be a variation of the Pythagorean identity, but I'm also noticing that sine squared theta minus 1 could be factored as a difference of squares. Sine squared theta minus 1 could be factored as sine of theta plus 1 times the sine of theta minus 1. And I like this approach a little bit better than using the Pythagorean identity because I'm looking ahead to what I want that numerator to be, right? I want that numerator to have a sine of theta plus 1, and you'll notice that by factoring, I just created that, didn't I? So I'm hoping that that works to my advantage. Let's take a look at the denominator. In the denominator, I have tangent of theta times the sine of theta minus the tangent of theta. There's a common factor, and that factor is the tangent of theta. So I'm going to factor that out, and when I do that, I'm left with the sine of theta minus 1. Put my equal sign. Did that help me? Yes, that helped me a lot. That sine of theta minus 1 in the denominator can now cancel with that whole sine of theta minus 1 in the numerator, and that leaves me with the sine of theta plus 1 in the numerator, and looks like the tangent of theta in the denominator, and you'll notice that that is exactly what I wanted it to equal. And so I'm going to write as my last line that final thing where the left equals the right. You might want to even get rid of your line down the middle and give yourself a big check mark and say, yes, this really is the identity and we have verified it. Let's try another example. Verify the identity cosecant of x plus the cosine of x times the cotangent of negative x. Does that equal the sine of x? I'm going to begin working on the left-hand side because that certainly seems to be the more complicated side. And the first thing that I'd like to do is maybe rewrite both the cosecant and the cotangent in terms of sine or cosine. So the cosecant of x turns into 1 over the sine of x plus the cosine of x times, now let's talk about this cotangent of negative x. Cotangent is an odd function, and in an odd function we can get rid of the negative inside that angle by pulling it to the outside. So I'm going to call that negative cotangent of x. All right, and I'm working toward getting all of that left-hand side to equal the sine of x. So on the next line, I'm going to write the 1 over the sine of x, 1 over the sine of x, and I'm going to move that minus sign out front. So the minus sign is going to be right here, and I'm going to have the cosine of x, and I'm going to rewrite the cotangent as cosine of x over the sine of x. Okay, so now let me go ahead and do that multiplication. So 1 over the sine of x minus cosine times cosine is cosine squared x all over the sine of x. All right, so that looks a little bit better. What else can I do? Remember, I'm trying to get this to equal the sine of x, so that denominator is going to have to go away at some point. Speaking of the denominator, I notice that each one of these denominators is the same. So I could rewrite this as 1 minus cosine squared x all over the sine of x, couldn't I? I just combined those numerators. And now it looks pretty good. 1 minus cosine squared x, well, that's just a variation of the Pythagorean identity, isn't it? I could rewrite that as, I think I'm running out of room here, so let me just rewrite all of that numerator. Let me rewrite that as sine squared x. And I like that a lot because in the numerator I have the sine of x times the sine of x. In the denominator I have the sine of x, and so one of those is going to cancel out, and I'll be left with the sine of x certainly does equal the sine of x on the right. So we've proved it. And we'll try one more. Verify the identity, the sine of x plus the cosine of x, that whole quantity squared, does that equal 1 plus 2 times the sine of x times the cosine of x? All right, so do we want to work on the left or do we want to work on the right? I think working on the left looks more complicated. And I put this example in because I want to remind you what it means to square something. What that means is that that thing that's on the inside, the sine of x plus the cosine of x, needs to be multiplied by itself. Needs to be multiplied by itself. Okay, so I have to FOIL, don't I? So I'm going to say sine of x times sine of x times the sine of x, which is sine squared x, and then sine of x times the cosine of x, so plus the sine of x times the cosine of x, plus, I'm going to do the inside terms. Now I can rewrite that as cosine of x times sine of x, or I could call that simply the sine of x times the cosine of x, which I think I'll do so that they look the same, right? We've got some like terms here. And then finally, cosine of x times cosine of x is plus cosine squared x. Okay, that was a lot, wasn't it? But a good thing came about. Sine squared x and cosine squared x, right? Addition is commutative. So let me just rewrite this. I could rewrite this as sine squared x plus cosine squared x plus sine of x times cosine of x. Now we've got two of those, don't we? Those are like terms. So this piece, that's one of those, and this piece is the second one. That's where that 2 is coming from. But notice here that we have the Pythagorean identity, don't we? Sine squared x plus cosine squared x is simply 1. We already know that that's true. And so if I rewrite that as a 1 and then just hook on the 2 times the sine of x times the cosine of x, I think, do you remember what we were trying to get that to equal? I think we've done it. Let's see if I can squeeze that in. Whoop, I think I got it in there. And sure enough, that checks, and I have verified that trig identity.